This presentation is called Considering Simple Triangle Vision Perception with Eye Movements in NARS. And so I came up with the idea for this presentation when I was reading Donald Hebb's book. And I got to the section where he talks about the self-organization of neurons for perception. And he brought up like the simple, like pretty much the simplest possible example of perception or visual perception, which would be like recognizing a simple pattern, the identity of a simple pattern. In this case, it's like a triangle. And so I thought, this is kind of interesting, the things he's saying. I can kind of relate them to what I've learned about NARS. And so I tried to kind of reinterpret that section from neural organization to conceptual organization, kind of considering what he said from a NARS perspective. So these aren't necessarily my ideas. These are Hebb's ideas, just sort of reconsidered from a NARS perspective. And in particular, the main idea is how eye movements are used for vision. So just some background about vision in NARS. So we know that usually for machine vision, we use neural networks, like a particularly convolutional neural network usually. But there's also the open question still of how far can we take the logical AI approach to vision without using neural networks at all, which would be really nice for NARS, since an integrated system comes with all of its own issues due to trying to integrate separate systems. So if we could have vision ability in just NARS alone, that would simplify things in a sense. So a NARS theory of vision perception was first introduced in 2018. And in 2019 in the sensory motor in NARS and perception in NARS papers. The main ideas were introduced there, but it still required more concrete implementations and experiments. And particularly relevant to this presentation, in these papers, the idea of moving your sensor. So you have obviously sensors and motors. So like your sensor would be like your eye, and motor would be like your muscles. But the eye itself does have muscle attached to it that allows you to move your eyes. So it's sort of a mixture between sensor and motor, or a sensor controlled by a motor. And so these papers introduce an operator called shift, which could be like a built-in operator for a NARS with a vision sensor. And shift would be used to shift vision sensor. So this is effectively equivalent to eye movements. So then in 2022, we actually ran some experiments for vision using just a pure NARS system, and got some numbers for a standardized data set, the MNIST handwritten digit data set. And NARS was able to achieve 44% classification accuracy for classifying images of handwritten digits that it's never seen before. So obviously 44% is not state of the art when you compare it to neural networks that have done that task. But it might be state of the art for symbolic systems. I'm not sure. I couldn't find other symbolic like reasoning systems that did this, but it might be out there. So while the result's pretty far from perfect, it's still better than random chance. So for a random chance, which NARS wouldn't necessarily be doing as well as random chance, since it has to execute operations to do anything. So it might not execute any operations at all. It might get a 0%. But if it was doing random, like random chance, you would expect like a 10% accuracy, since there's 10 digits, 0 through 9. But we got 44% classification accuracy, which says to me that NARS vision seems like it could actually be feasible, even for a real world, like useful application, like image classification or optical character recognition. And in that experiment, we used a static vision sensor, which means basically the eye was just fixed, and an image was presented to the eye, or the camera, and there was no eye movements. So instead of eye movements, there was a spotlight window. This was a window of attention which moved around the visual field. So there was like a movement in a sense as the attention window moved around, but the actual sensor was fixed, and so the visual field itself remained fixed. So in his book, Organization of Behavior, Hebb discussed the neuropsychology of triangle vision perception using eye movements. So basically a dynamic vision sensor. And like I said, we're going to try to consider these ideas from a NARS perspective, just at a very high level. Um, and then maybe these ideas could be made more concrete and explored and tested in concrete experiments in the future for NARS vision, for example, to improve the accuracy score on MNIST data set. So just a couple assumptions that are made here. First of all, that lines in their orientations or their rotations are taken to be the fundamental components of vision. So if you look on the right, this is basically a representation of um, the visual cortex in the human or the mammals. And this is kind of apparently what it looks like. So across the entire visual field, the neurons are basically kind of acting like feature detectors. And what they're detecting is there a line, the presence of a line, and then also what is its rotation. And it kind of does this across the entire visual field. So you'd probably want something similar for NARS, some sort of um, like uh, image filter, like a canny edge detector or something to perform edge detections. And that this would be like your primary sensor. Because from these, when you have these lines and you have their rotations, then you can build up more complex perceptions from them. Is this actually the full story? Probably not, because even these are actually learned features in humans and like in brains. But we can take it, but it's such a low level that we can probably take it as like the fundamental unit for building up more complicated perceptions. And the lines are also important because they guide the eye movement. So they're not just important for, features are made out of lines, they also guide eye movements. So when there's a line in your peripheral vision, it arouses a motor response for your eye to move in the direction of the line. And basically what this does is when you look at an object or like a new object, you will follow the contours of the object or the edges of it just automatically. And this helps you to determine the figure versus the ground. And so we're going to consider three separate aspects of vision, or not separate, but three aspects of vision, using the triangle vision for a simple example. The first is learning expectations through your eye movements. The second is the problem of sensory interference. And then third is the case of variable distance from the stimulus pattern. So first, learning expectations from eye movements. So here's the triangle example. So there you have a triangle here with three corners. One's labeled A, one's B, and one is C. And the idea is that the system can move its eye at least between the three corners in the simplest example. So here it's like fixated on corner A. And then this is like supposed to be in the shape of the eye for understanding. It might be like more circular in like a real application or something, because this is kind of a difficult shape. But this red circle represents the central vision or the foveal vision. And this is basically where the visual feature is perceived. And then between this red circle and the purple circle is the peripheral vision. And the features here aren't going to necessarily be perceived, and we'll talk about why. But they're actually going to be used to, like I mentioned earlier, guide the eye movements. So right outside the foveal vision, there's two lines, and they each have about an equal influence about what direction the system's going to want to move its eye. So there's a line going this way, so it might go 50% chance to move up here. There's a line going down to corner C as well, and there's a 50% chance you might move there. So yeah, in this image, it's focusing on A, and then it may move to B or C as it perceives the figure. And so for it to move, say to the corner A and then down here to corner B, so it's moving up along this line here. NARS might use an operation like shift, which we talked about earlier, and it might have some arguments in the operator. So say like shift upright, or it might be a quantity for more precise eye movements. But just for the simple example, we have shift upright. And then, so when this happens, it's gonna be very fast. So in the NARS memory, or in the buffer at least, you're going to have some sensory events or some activations from corner A. And then after a very quick eye shift up to corner B, there's going to be new sensory stimulations from corner B, causing different activations. And so since we have these concepts or these events from A and B being activated in very quick succession after the eye movement, then NARS can form an expectation between them, obviously, using temporal induction. And so this forming of expectations from these eye movements is like akin to NARS memorizing pattern, not just specific features from the pattern, but again, like the contours of the pattern in a sense, where it's moving, the different parts of the overall pattern. And so this is interesting because given a certain corner or a certain visual feature like this corner A, then the expectations inside the system, once it's learned them initially, it will allow NARS to predict the other features. And so conceptually, this is what your expectation would look like. It's an implication statement where you have something like this visual feature, and then shifting my eye, I expect to see this visual feature. If I shift it in this way, then I expect to see this visual feature. So this is just like a visual example. Obviously, you can't actually have pictures like this in NARS, so it's going to be different. And more concretely, they're going to be logical compounds created using the conjunction, disjunction, and negation. And so in the simplest case, you might just take a conjunction of all the pixels. So say here, these lines are the activated pixels. Like each pixel on these lines are considered active, so they have a frequency above 0.5 because there's an edge detected there. Then the simplest case would just be take a conjunction of all of them. So when I'm looking here, the visual feature is all of the edges anded together. So it's basically a kind of a pixel perfect, in a sense, feature. And now the problem with that is that in a more realistic scenario, NARS will probably not encounter the exact same stimulus pattern or that exact same feature because of changes in lighting, or slight changes in rotation or shifting of the feature. And there also might be more possible fixation points. So NARS might fixate slightly to the left or to the right. And so you might not actually ever encounter this exact same conjunction again, this exact same compound. And if you just want to do the math, especially if you have even like a low resolution central visual field, 10 by 10 pixels is very, very small. But even with a 10 by 10 visual field, and only binary activation, so a pixel is either 0 or 1 only, not even talking about like color vision or anything like that, or values in between 0 and 1. Even with only binary activations, this small patch of pixels is going to have a huge number of possible combinations. So you're very unlikely to come across, if you do a conjunction at least, the exact same sensory scenario. And so what you probably need to do is, other than keeping your central vision window small, you also need to extract feature compounds so that they're more general or more abstract, which makes them less specific, which is somewhat bad also, but also good because you can recognize them in more contexts. And so there's like 3 different methods that I thought about that you could do this. So the first would be to stretch the truth. So we know that all the now truth values are just a matter of degree, so that even if a pixel has a low activation, so if it has like frequency 0.6, which is still technically true, just very, very low truth, or even if it's technically false at a frequency equals 0.4, although sort of towards the middle, they still have some degree of truth to them. So if it's really necessary, it's kind of like squinting your eyes when you look at a pattern. You can use these in feature compounds, but the inclusion of sensory events with very low truth values is obviously going to lower the compound's truth value, the overall truth value. But you can still do it in a pinch. The other option is to take subsets of visual features. So when you have the more pixels and features that you're including in your compound, you're making your compound more and more specific. If you say it's this pixel and this pixel and this pixel and this pixel, you're going to have a very specific compound, which again, you might not encounter that in the future. Whereas if you only take a smaller subset, say just these 2 pixels is what I'm interested in, then that's a compound that will be recognizable in more scenarios, more context, simply because there's less features that need to be active. So rather than just taking your whole 10 by 10 central vision, you might take a smaller patch of that 10 by 10, so a smaller subset of features. And then finally, you could use disjunction, which is different from conjunction. Disjunction means or, and so that's going to encapsulate a larger number of scenarios than the and operator. So, if you have a compound that says, okay, this statement is true whenever pixel 1 is active or whenever pixel 2 is active, that's going to be true in a lot more scenarios than a compound that says, well, I'm only true when pixel 1 and pixel 2 are both active at the same time. So disjunction allows a compound to be true in a larger number of contexts or scenarios. So the basic idea is just to learn implication statements, um, implication statements through the I movements. But again, you're going to have a problem with recognizing features. And so you need to strike a balance between generalizing or abstracting the features enough to recognize them in various contexts, but also keeping them specific enough that they're still going to be useful for recognizing the pattern. Because you could have a very general feature that is active in like every sensory scenario, which that's not going to be helpful either. And so what it means for them to be useful for recognizing a pattern means that there's not too many, but also not too few possibilities. So if you have tons of implication statements and expectations, the more implication statements that a visual feature is in, the less useful it's going to be for recognizing the pattern because NARS doesn't know which expectation to follow. Whereas the less expectations a feature is in, it's going to be more specific because if you only have, say, one expectation, one implication statement, it's going to be a highly specific scenario, but it's going to be not perhaps so useful for identifying the pattern in different contexts because it may never come across that exact specific feature or expectation again. So you don't want to necessarily memorize pixel perfect features either. And so that's about features, but then there's also like feature generalization, but there's also the problem of ambiguity. So, for the triangle, if you just had a triangle, I guess it's okay. But if you add, we can add another shape to the mix. So let's say we have this square, this diamond shape, which you can see on the image to the right. And so you'll see that both figures, both the triangle and the square, have this feature P. So if I'm just looking at this feature P, I won't necessarily know what am I looking at. I don't know if it's from the square. I don't know if it's from the triangle. Same with this. This is corner A, and then same with this feature Q, which is this edge between corner A and B. That's also common between the two figures. And so just looking at those features alone, we can't really tell what figure we're looking at. On the other hand, if we're only considering these two figures at least, this feature TB1 and TB2, these are highly specific to the triangle figure. So if I see even just this one feature, TB1, I already know I'm looking at the triangle or TB2 and not the square because the square doesn't have these features. Now, of course, NARS can't determine which features and expectations are going to be useful up front. And so those need to be refined. And also the evidence aspect of now solves part of this problem automatically because NARS is going to be from the various visual features deriving and pooling many different possibilities about the identity of the figure, and they're all going to have different truth values. And so when giving an answer, NARS can just select the one with the highest truth value or the most evidence, especially for executing operations. So just for a concrete example, let's say that we're exposing NARS to the triangle pattern and the square pattern. And with each pattern, we're giving it the label. So when we show it the triangle, we're saying this is a triangle. We're showing it the square, we'd say this is a square. And we give it these labels so it can form the associations. So then in the future, then we show the patterns again, and we're trying to say, okay, NARS, what is the identity of this figure? And so it might look at, say, figure P, and it's going to derive, it'll have seen figure or feature P in both contexts for the square and the triangle. So it's going to derive the label square and it's going to derive the label triangle. So it's sort of ambiguous. And there's like two options in its head. What could this figure be? Now, at least we know it's not going to be a circle because these are lines, not curved lines. So at least some figures can be excluded, but at this point it's still ambiguous. But then when NARS looks at a different feature like this TB1, that's going to derive only is triangle. And not is square. And so this label is square is going to have a lower truth value compared to is triangle. And as NARS looks at the figure for an extended period of time, say it's looking at this triangle, some of the features might be ambiguous, P and Q, but then these other ones are going to be more identifying, this TB1 and TB2. And so there's going to be more evidence on the whole for the triangle label than the square. And so that's how it could correctly identify the figure. And this was the basis behind the MNIST experiment. And so these singular features can be useful for identifying a figure. But with the eye movements now, because we're talking now about adding eye movements into the vision, then NARS can additionally use these confirmed expectations and anticipations for identifying the figure as well. So if this feature P is just too ambiguous to make a full prediction, and let's say even this feature that we said was very specific to the triangle TB1, in the simplest case where we have the triangle and the square, yes, that's true. That will help identify the triangle. But in a more realistic scenario, this could belong to any other number of shapes. This could be like the fin of a shark or something. So it's not necessarily we can just look at one feature and say, yep, that's a triangle. But if NARS does start at P and then performs an eye movement and sees TB1, now it's going to be more confident that it's seeing a triangle because it says, okay, I saw this feature here. And if it's a triangle, then this other feature should be located at this part in space. So let me move my eye and look. And then when it looks, if it can confirm that, then it can say, okay, yep, this is a triangle. And if there's many confirmed expectations, now like one time is good, but if you do this many, many times, then it will become more highly confident about what the figure is. It says, okay, and now I move my eye down to C, I expect to see this type of triangle shape. And if it does, then I say, okay, I'm almost certainly looking at a triangle. And then finally, there is the case of differing distance from the stimulus pattern. So obviously, in an actual realistic scenario where the agent is embodied and moving around the world with its vision sensor, the agent is going to be almost always at a different distance from whatever the stimulus pattern is. So as it moves around the world, it might be closer, it might be further away. So if, like on this image, this pattern is very far away from us, which is why it looks small. And then this one here is larger because it's closer. And so you can see that the two figures are, they're the same, they're similar, but they're going to be creating a different sensory impression on the retina, on the eye, simply because they're larger. So it's going to be activating different neurons. So the question is, so how then do we see that these two shapes are the same if they're doing a different activation in our eye? And here, again, the idea of eye movements and corners or lines is very important because it gives a good reason why to focus on corners in central vision and lines in central vision and to sort of ignore the peripheral. So if you look at this image to the right, the red circle again indicates the central vision. And look at the features inside the central vision when the pattern is far away. And then on the right, when we're closer to the pattern, look again in the central vision. Both of these eyes are fixated on corner A the whole time, and yet it doesn't matter what distance you are from the triangle because the pattern in the central vision is going to be exactly the same. So the visual features are going to be exactly the same, which means that NARS could match this pattern regardless of the distance from from the triangle. It can match that and say, okay, well, this looks the same. It really won't even notice too much of a difference, at least when it comes to central vision. When it comes to eye movements, you might have to move your eye quite a bit more, so that's a different story. But at least for when it comes to the image features, they're going to be the same in central vision. And this is true for any rectilinear pattern, and rectilinear means a pattern composed of straight lines. And so this kind of makes the issue almost moot, since it doesn't really matter how far the agent is from the shape, as long as it's fixating on the corner. And there's also, while the pattern outside the central vision changes, it changes predictably. So you can see that this line, as we get closer from A to B, extends outward. And then as we get further away from the shape, the line comes back inward, which is why it looks smaller. So the pattern in the peripheral vision, the line changes predictably. And what's cool about this, the fact that the two central vision patterns are the same, this introduces a form of stimulus equivalence because the two stimuli are technically different, but they can be recognized as having the same features in the same identity, which is triangle. Now, for curved figures, it's not going to be quite such a simple answer because the pattern in the central vision will change with the distance to the overall pattern. But we can, you can partially resolve this problem by choosing to fixate on corners and straight lines in your system design, and sort of ignoring the larger curved patterns. So in conclusion, the eye movements, or doesn't necessarily have to be an eye movement, it could be the entire head. But the movement of the visual sensor is important for vision because it allows the agent to focus on different parts of an object using the same sensory cells. And there's three aspects of eye movements that we want to consider for NARS vision. The first is that during eye movements, the system should be forming expectations in the form of implication statements with the operation, and that will allow it to make predictions and perform pattern recall. The second aspect is sensory interference occurs when features obscure the identity of the overall pattern, but the system can learn to effectively ignore sensory interference over time by refining its expectations. And then finally, the distance from a pattern changes how the pattern appears, and that can also obscure its identity. But the system can overcome this by focusing its central vision on rectilinear parts of the pattern using eye movements. And my hope is that by enhancing NARS with eye movements, it'll have the possibility to improve NARS native vision, and especially to improve the score on standardized data sets like MNIST digit dataset. And that's all. And here are my references. And thank you very much.